So in the last video, we met the interest compounded continuously formula, and we had a lot of questions about it. For example, what is that number e? What's it doing in that formula? How the heck does the interest rate go from being in the multiplier to being in the exponent? Well, let's start by talking about that number e. The number e is an irrational number. So we can't write it as a terminating decimal. We can't write it as a fraction. In fact, we can't even write it as a root or something, which is a common place that we meet irrational numbers. E is kind of like pi in that way. It's an irrational number that is not the solution to any polynomial. It's just there. Like pi, e is defined to be the number that works in certain formulas. The definition of pi is that it's the ratio of a circle's circumference to its diameter. That is, it's the number that's going to work in the circumference formula. This 2 is just here because we typically talk about the radius rather than the diameter of a circle these days. But pi is the number that when you multiply it by the diameter of a circle, you get its circumference, the distance all the way around the outside. We usually think that pi is about 3.14, but that's not its exact value. That decimal just continues without repeating forever. E is defined in a similar way. Pi is the number that works in the circumference formula. E is defined to be the number that works in the interest compounded continuously formula. But, that's kind of an unsatisfying answer. Because shouldn't the base in that interest compounded continuously formula, shouldn't that depend on r? How does r get from being in the base to being in the exponent? And then our base is just always the same. Well, there's a little bit of algebra trickery involved, and I'm going to show you the algebra trickery so that this makes some sort of sense. We're going to start by looking at the regular compound interest formula for interest compounded n times. And the p0 part just sits there. The p0 part is the only thing that's the same between the compound interest formula and the continuously compounded interest formula. So we're just going to look at the exponential part. Okay, now, this next move is one that it wouldn't necessarily occur to you to make, but I'm going to tell you that this move works and then show you how it works. This is not a demonstration that I'm going to ask you to reproduce. Your job at this point is to follow this and understand what's going on. The move we're going to make is to introduce a new symbol, x, that represents n divided by r. Which is weird, because that isn't even anything that shows up in this expression we're trying to manipulate. But then the r over n part is equal to the reciprocal of x, and the n part is equal to r times x. So that means we can rewrite this expression in terms of an x and without an n. We have 1 plus 1 over x to the nt, so r times x times t. Why do we want to do that? Well, we can have something with just an x in it that we're now raising to the rt power. This is how our interest rate gets into the exponent. Because now when we're thinking that n is very large, well, that's when x is very large, right? X is just n divided by something. So if n is a very, very large number, x is also a very, very large number. And so now we ask what happens to this expression, 1 plus 1 over x to the x power, when x is a very, very big number. Well, let's use our calculator and see what happens when we plug in very big numbers for x. I'm going to use the table function. So I have 1 plus 1 over x, all raised to the x power. And I'm going to set my table to ask and enter these first three x values that I have here. When x is 10, this gives me a value of 2.5937, etc. When x is 100, this gives me a value of 2.7048, etc. When x is 1,000, this gives me a value of 2.7169, etc. Just keeping 1,000 here for reference. And then I'm going to put in 10,000 and 100,000. When x is 10,000, we get 2.7181, etc. When we have 100,000, we get 2.7182, etc. And so it's easy to see that this is getting close to something. The bigger x gets, the less this changes every time we go up. It's getting close to something. It's not getting close to something obvious like 3. The number it's getting close to, we call that e. And indeed, if we tell the calculator to tell us a decimal approximation for e, so we take just e to the first power on the calculator, it's about 2.7182, etc. We do see that this list of numbers is getting very close to that. E is defined to be then the upper limit on that sequence of numbers that we get with bigger and bigger values of x.